Hi, this is the third video of a series of videos on how to model a reinforced concrete beam in Abaqus. Before we start anything, on the previous video I meshed the part with a size of 0.25 inches of a quarter inch. That ended up being too small, and what that does is that it will take about 6 hours to complete the analysis on a quarter of a beam, a quarter of the model. So what you need to do is change the mesh size to something bigger and run the analysis, and from the visualization module see if the results make sense. Once you're sure that the results are close to what you need, then you can go ahead and change the mesh size to something smaller. The only reason for you to do that is because you will see more clearly crack patterns on the beam itself. So to do that, go to the model tab and then beam, highlight beam, and then you're gonna go to mesh, and then you're gonna change the seed size, go a little higher, 0.75 inches. Even half inch is appropriate, but I'm gonna go 0.75 inches since I've already run the analysis. So once you do that, apply and then click OK, and do the same thing with the rebar. Go to change it to the highlight the rebar part, go to seed, part, change it to 75, apply, OK. I'm gonna cancel this, and then you go ahead and mesh the parts. Mesh part, okay, the mesh part, yes. I'm gonna click no because I've already meshed it, and do the same thing for the beam. Mesh part, okay, yes. But what this does, if I would have clicked on yes, it would have tell me something like error meshes. Deleting the mesh is gonna delete sets associated with that mesh. So just click OK, and what you have to do is change this set and this set again, because when you mesh these were based on the previous mesh. Now you have to change it to make it match your existing mesh, and I've already done that. So you do the same thing, double click on one of them, and or right click and click edit, and then it says reselect the elements for the set. Then you reselect the elements for the strain, and then another one for the displacement. I mean for the load. No, the displacement, the load bar stays the same because it's geometry and that didn't change. The displacement is the one you have to change, but that's easy to do. And once you're done, I'm gonna press escape to exit. You go back to the job module, check it, and once you check it, then submit it. And you may get errors like the excessive distortion. I guess it's normal because once the concrete cracks, it loses all, it becomes fully plastic, and then that's why Abaqus thinks that there's excessive distortion in that element, but that's okay. The analysis will run and complete. So once you're completed the analysis, you click on results, and you can change the variables. You turn them on from here depending on what you want. Deform, the deflection, which is U, and the Y direction is this one. With the plate buttons, you see how the deflection progresses as the analysis advances. I'm not on the deflection, I'm sorry about that. This is the deflection. So this is how the beam is deflecting. That's full deflection. U. And this is the magnitude. It has to be primary here, so you can see the magnitude. The only thing is that it's difficult to see. This is the ODB, or the output database file, and it's stored in temp. whatever you want to get out of this module for this particular run, you gotta get it now, because if you close Abaqus, then the ODB disappears, and then you have to rerun the analysis again. So from here you can do a quick check to determine if the results make sense. But for if it's if the wing hasn't deflected, for example, and you start running the frames to see how the deflection works, and the beam not only goes this, but it goes into the page or out of the page, it means that your boundary conditions weren't properly prescribed. Or if you render it as wireframe, let's see. Let's go to stress, the Mises stress, run it. That's the maximum. If we go one step at a time, it's easier to see how the stress develops in the concrete. And after that, it stays not constant, but you don't visualize that much after that. Only in the top, the compression. You can also make annotations if you want. From the viewport menu, create annotation, and then you can choose arrow and text just like what you do with AutoCAD. And then pick arrow target. Let's pick this. No, here, anywhere. There. And then just drag it and put something like von Mises stress preview. Okay. And then you can go to file, print, and then print to file, PNG, stress result as the name. Click apply and click OK, and then yes, click just. This is store and temp. Let's find it real quick. So let's see temp, and where's that PNG file? Here, let's just preview it. And there it is. And you can use that for your report, your presentation, and so on and so forth. So now let's close this one. Now we need to create our XY data pairs from the analysis, which is what we're after. That was the whole point of the analysis, to determine if our model matches our experimental results. So click on Tools, and then XY data, create, and then it's ODB history output. Click Continue. And we get a whole lot of choices here. We're gonna start. There's only two variables that we need: strain and force, and they're both plotted against the displacement. So let's start with the force. Select all the reaction forces, and then click on Save As, and it's a sum. The sum is going to be called force, and that's a quarter of the full force of the model, and that's how it gets plotted. It looks pretty close to the experimental one, And then for the displacement, just save it as the displacement. Click OK. And now we need to find this strain. In the X direction. I don't see the strain. I'm sure we did set it up with our set we created, but let's check real quick to see if we did or not. Go to model and then history output request. Strain, edit, set compression E11 strain. So it should have wrote it to the database. Total strain component E11. So let's see. Let's go back to job and then results, tools, XY data, create. It's still ODB history output. Oh, here. E11. Okay. Save as strain. This is compression strain, so we'll save it as compression strain. Click OK and dismiss. Now this is where we create our report, or load versus displacement and strain versus displacement reports or graphs. Go to tools again, XY data, create, and then operate on XY data. Click continue, and then we're gonna pick the operator here. So we're combining 2 pairs of data, which is the displacement, but it's gonna be -1. In this case, our displacement was positive in the negative y direction, but Abaqus takes the positive and the negative y direction as negative. So I just have to change that, so it's -1 times the displacement, and then you just double click on the displacement, type comma, and then it's 4 times the total force, because we're only modeling 1/4 of the beam. So this force is only 1/4 of the total force. And then plot the expression to see if it makes sense. It does. And then we'll save it as force versus displacement. Click OK. And then let's clear the expression. We've already got one, and let's repeat it for the strain. So it's gonna be -1 times displacement. We may not need that negative, but we can compare it to our experimental results, because right off my head I don't remember how we plotted it, but for now let's leave it like that. And then strain, plot the expression, save the expression as strain versus displacement. Click OK. Okay, so now clear expression, cancel. Go back to tools, XY data, manager, and then select force versus displacement, the one we just created, and click on edit. We only have 3 pairs of data, which means that our initial let's go and check that real quick before we do anything else. That's gonna be on the step we created, edit. No, it's actually the history output request. I'm sorry about that. Let's go back to the history output request. It's gonna be the same problem with this one, and this one. So let's pick one of them. Edit. This is the problem here. We put that the Abacus should write a point every 100 points and on the database. So we need to change this to something smaller, say 10 or even 1. But if we do that, then we have to rerun the analysis to get more data points. And you can do that by yourself. You just go back and change it to 100, click OK, and do the same thing with the force, and then we do the same thing with the strain. And let's check the history output created. This one was the default and it stays as 1, so that's fine. So let's go back to job results, and let's go back and import our data into Excel and superimpose that curve into the existing experimental curve and see if it matches our results. So go to Tools, XY Data Manager, and then select force versus displacement, edit, and you'll get this spreadsheet. So select all the values, control copy, and then we go to our experimental results and paste them anywhere. Control B. This, copy. This is the okay, it's the other way around. Let's do this. And now let's add the data into this existing graph and see if we get something close. Let's call this Abacus. Displacement is this. Click enter. Force is this. Click enter. Okay, but now we need to go negative. The force should be positive. Cancel. Let's do this real quick. Negative 1 times this. Okay, and let's try again. Maybe what needs to be negative is the displacement, since it's going in Abacus, of course. But we don't worry about that. Well, let's check if the general shape is right, and then we'll try to fix that later. Or X values, displacement. Let's try again. Abacus, displacement, enter. Force is in this case this one. Click OK. Click OK. This is the problem with the history output request, this straight line. This is the origin, so the only thing is plotting is 0, and then this point here at 1.5, and then this point at 2.8, and then this point at 3.3 inches. So if we get change the n on the history output request, we should get way closer than this. Maybe up here higher, and then it's gonna decrease. But as you can see, this is the general shape of the load versus displacement curve for this particular concrete beam. It's not accurate because we didn't change the end, but if we were to do that, you'll get a lot closer, which will be, let me see if I can find it. I don't see any curves. So these are trials, but this is how it has to look like. This is the diamonds are the experimental ones, and these are abacus runs. So it has to be something closer to this. Right now we're going from here to here, and maybe to here, and maybe going down a little bit with the result we just got, which is, say, the general shape, but it's not quite right. But that's what you have to do. You have to change the end on the history output request and then run it again, and you'll get this general shape. Let's go back to abacus. And then you can do the same with the strain. Edit. Copy the values. You're going to have more than this. And then superimpose them on your strain versus displacement graph if you have strain numerical experimental results. So cancel that, dismiss. And now let's start looking at the crack patterns. These are the active yields, tension, and as the analysis progresses, you can see it increasing. And it's pretty raw because you have the mesh is 0.75 inches each cube. So if you decrease the mesh size to say ½ inch, you're gonna increase your analysis time by like 3 times. But it took like 10 minutes to run this analysis. If you decrease it like we did on the previous video, that we're gonna go with 1/4 inch, it had been like 40 minutes and it was only 10% complete. So if you want to be that accurate, then you can let it run overnight, and maybe by the time you wake up the next day, the analysis will be complete. So that's the active yield, and then the tension damage. You can see tension damage on the concrete as it progresses. The full cycle. All these have it has failed. And the closest we're gonna get to crack patterns is you can go through each one of them as you go. Let me go back and do this. PEQT, the total plastic energy. That's the closest we're gonna get to crack patterns in abacus, and it's gonna be pretty rough too. You can see the cracks develop as you run the analysis. These are deemed to be cracks, but they're kind of rough and they're kind of evenly spaced, and that's not how it's gonna be in real life. But if you refine the module, you should get the model. You should get something closer to real life. Where do I have that? My actual crack patterns. So let's see. Where is that? This is the actual one. This is the unreinforced beam, the actual lab beam. We got this picture. We took some video or pictures. We digitized those pictures, imported them into Photoshop, and then we did some little trick in Photoshop that actually gives you the actual shape of the cracks and the outline of the beam. That's all we were interested in, and you can see that it closely matches the actual crack patterns on the beam. The model matches the crack patterns on the beam. They're more closely spaced here in this area, and then they start getting farther from each other as they get closer to the supports, which is the case here. And you get that by decreasing your mesh size, and that's gonna have the side effect of increasing your computing time. So that's what it is. Let's close that. That's the full crack pattern deflection you're gonna get at a displacement of 3 inches. And that's it for the tutorial. Abaqus is pretty powerful. You can use it to model, say, beams, which is, this is the case, but you can change the material to, say, concrete. Not concrete, masonry, if you specify constraints between the bond of each concrete, or you can make it steel, or you can make it wood for concrete. You can turn it and make it into a beam, a column if you want. So you can go from here, you can do lots of things. And like I said previously, we may end up doing, I'll probably do it next month and so on, put an FRP on the bottom and determine the difference between, those are the reaction forces, how much it deflects with the FRP and how much load it, what's the increment in load carrying capacity of the beam with the carbon fiber plate or the natural fiber plate that we will attach to the bottom of the beam. That creates extra steps in the analysis where you have to create the FRP or the natural fiber reinforced polymer. Then you have to create a contact condition between the FRP and the beam. You have to debate whether to model that contact interface as a layer of glue, or if you wanna completely exclude the glue from the analysis, which I think is appropriate based on what I've read. It doesn't affect the results that much. And then you have to monitor strains on the plate itself and strains on the concrete, because the plate is going to help the concrete carry more compressive strain, so the tensile strains are going to be less, and so on and so forth. So take it from here and do I know this model, the model and the material parameters we inputted are not perfect, but it's your task to make it better. You use it as a reference in case you have problems. I don't think I'll be able to help with individual questions, but take it from here and do read the documentation. The documentation has lots and lots of useful information. I've read it a lot. It's hard to read, but it helps out a lot. So if you click on something and it takes you somewhere else, don't skip it, read it. And then if it's gonna take you again to something else, read it still and keep reading. Even if it's not related to your particular mod, you'll learn more and you'll become more comfortable, at least with using AutoCAD. So I hope this helped you learn a little bit about at least this type of analysis, which is based on civil engineering. This is the type of work we do at Cal State Long Beach, and I hope you enjoyed the video, and I hope you keep on learning. So have a good one and keep using Abaqus.